Ok. Então, boa tarde, pessoal. Nós vamos dar sequência a mais um dos nossos seminários. E hoje a gente convida aqui Lisa Sturm, que vem da Technische Hochschule Nürnberg, na Alemanha. Ela está fazendo um estágio aqui com a gente. Passou alguns meses aqui conosco, né, e ela está se despedindo de nós hoje também. E ela fez um estudo muito interessante que fala sobre a metalização, a otimização da metalização frontal de células fotovoltaicas. Então eu vou passar a palavra diretamente para a Lisa. Lisa, foi um prazer ter você conosco aqui. A gente gostou muito da sua visita. Espero que você tenha aproveitado muito o seu tempo aqui conosco. Aprendido bastante português também. A Lisa vai falar inglês porque ela está um pouco tímida com o português dela, que melhorou muito nesses meses todos que ela está aqui com a gente. Então, Lisa, você pode tirar a máscara se você quiser. A gente guardou as duas primeiras filas de distância. Todo mundo vai sentar mais para trás, a plateia vai estar de máscara, mas se você quiser, você pode tirar a sua, ok?
So, hi, my name is Lisa, and I will have a presentation about my time here. I investigated the optimization of the front metallization of silicon solar cells, and I want to give you a quick guide through it. So first I'm going to talk a little bit about me, like which university I come from, how I got here, then a short motivation about the project and the project itself and the idea behind it, the program we used, the simulation we did, and finally the results. So yes, I study energy process engineering in Nuremberg, and it is the study discipline is about the processes, how to gain energy through the process, and it focuses on renewable energies and also on the fossil and the nuclear energy program processing. And the institute is in Nuremberg in Germany, as you can see in the picture. This is our main building, and this tiny building here is our faculty. Our institute is very famous for his former headmaster in 1839, Georg Simon Ohm. He was the discoverer of the Ohm's law. Here you can see a small picture of him. Furthermore, I came through the RISE World program here. It's from a federal organization called Deutsche Akademische Austauschdienst, and it focuses on the band, or like the bands into the international world. It wants to strengthen them throughout these kind of programs where they offer scholarships to these internships. And my internship here at the laboratory was with the RISE Worldwide program, and this one is for bachelor students who study biology, chemistry, physics, or any kind of engineering. So it needs to be one of these technical things because it is a research internship. Normally the internship is in between the semesters, between July and September, but due to COVID, my stay was postponed to October. A little bit about the project, or what we're trying to do, was that solar cells or solar models are designed for standard test conditions, which basically means they are laid out for a temperature of 25 degrees and irradiance of 1,000 watts per square meters, and an air mass of 1.5. Here, for example, for this irradiance during the day, which ends in like 1,000 watts per square meters. And this is not really optimal for field conditions, especially here in Brazil, due to Lucas's research. We know that the over-irradiance is a big part in Brazil, or is a big influence factor in for PV models here in Brazil. It is possible to gain up to 1,800 or even more than 1,800 watts per square meters, which is high, way over the standard test conditions. And if you look here on the right on the table, these are measured over-irradiance data worldwide, and you can see that in the top 10, basically here, we have 7 out of the top 10 over-irradiance measurements are in Brazil. So in Brotas, we can see here that over or about 30% of the energy of the irradiant distribution is above 1,000 watts per square meter, so higher than the standard test conditions. And the model is laid out for. So what we know for a traditional silicon solar cell is how the efficiency, this one is a relative efficiency, how the efficiency behaves over this irradiance levels here up to 1,000 watts per square meters. But what happens after them, that we don't know. Like, does it stay constant, or does it go back, does it drop again? Did it have a peak point? That is something we wanted to investigate. So we wanted to figure out the rest of the efficiency curve, and also for that we wanted to figure that out for multiple bus bars to see if the non-used potential at these irradiance levels could be used. And then we wanted to find the optimal bus bar number to as you can see here, we were like optimizing them. We were like testing a cell like that by changing the number of the bus bars and finding the optimal point. So far the front metallization has two losses, or two responsible losses. First the shading losses, and then the resistance losses. The shading losses increase with the number of bus bars, and the resistance losses decrease with a higher metallization. So these two losses are working against each other, so you need to, or we needed to discover or calculate the optimal point for that. And we wanted to do that with the field condition for Brotas, and not only for the standard test condition, with the Brazilian energy distribution, including the over-irradiance. Which I wanted to mention, but is not really relevant then, the screen printing technique, like the front metallization of silicon solar cells is produced with the screen printing technique, and that's like a very cost-efficient change for the format. So if there would be a different amount, that would be not as expensive to change. Yeah, about a little bit about the program that we use to simulate these solar cells. we used the free version of GRIDDLER 2.5. It also has a pro version, but for us the free version was fine. The program itself was developed 2013 by, I need to peek, Dr. Here it is, Jonathan Wong, and it is basically a finite element method which calculates the GeV curve of a cell, and yeah, with it different parameters like the efficiency, the fill factor, the voltage at the maximum power point. We were focusing more on the efficiency, but yeah, GRIDDLER has a lot of these yeah, things it could do. And we got the program at the platform GRIDDLER Solar. So GRIDDLER Solar was merchandised the program in 2018. We used a monofacial PERC cell for the investigation because it seems to be the cell that goes, or that becomes the most one on the market. It's not quite yet it, but it will be probably in a few years. And that's why we took that cell, and GRIDDLER was like offering the cell also in their library, so we could use that cell with these parameters, which are all fixed. We used an M-size wafer with 161 fingers, and the bus bars were changed. And yes, I'm going to walk you through one of the simulations to give you an idea what I did. This is the first page of GRIDDLER. It's basically yeah, modeling the shape and the size of the cell. Here you can see it. You could, or we changed the bus bar numbers here, and this one is for the rare side. But because we wanted to do a monofacial cell, it was very important to have uncross there the cross, so we could have a monofacial cell. We changed the bus bar number from 3 to 15, and the rest that we kept consistent. And after that you come to the second page of GRIDDLER, where you can change the resistance of the metallization and the illumination of the front side, which we changed from 0. Instead of like having the unit of watts per square meters, we had the unit of suns. So we had 0 to 1.8 suns to show 0 to 1,800 watts per square meters, and we did have steps from 50 watts per square meters, so 0.05 suns. And for every bus bar we designed, we needed to do 37 simulations to get the full data. And by clicking on the sweep button here, it generated the IV curve here and gave us a short output with the efficiency here in the middle, the fill factor, and the voltages. And in the end, we had a full report also from GRIDDLER with the losses of the cell included. For the results, I wanted to start with this diagram because it shows the efficiency of the number of bus bars at standard test conditions. So what we can see out of this diagram is that the most optimum point, or the most number of bus bars at standard test conditions, is about 5 bus bars. Sometimes 4, but mostly 5 here. And that's important to like have in mind for our conclusion later. So here we have the results of our simulation from GRIDDLER by itself. We have here the efficiency of the cell, and here we got the irradiation, which I mentioned before here, with the suns instead of the watts per square meters. And I wanted to like show you first the curve, how it looks like. If you see here the more fat blue line here, it is the line for 3 bus bars, and it shows how the efficiency curves looks like, how it's going. And you can see as well with 4 bus bars, which is the orange line here, which is a little bit bigger, that they have always the same shape. Just by increasing the bus bars, we also increase the efficiency by it, but the shape basically stays the same. So the higher the bus bars, the higher like the maximum point. So if at 4 bus bars, you see here in the end at 1.8, there was the maximum, and in, for example, 5, it would be around 2 something. And what you also that is like what we, this part is what we didn't know before, and that was what we knew before. And what you can also notice on the graphs is here, this little bump. It occurs here after 1,000 watts per square meters as well, and also like at some bus bar lines here too. This is the change of the voltage at the maximum power point. So mostly like here, here in between, the maximum power point was at 550 millivolt, and here it jumped to 575, and here the main jump was to 600 millivolt millivolts, yes. And the thing what we wanted to do now is you needed to see which bus bar or which would be the optimal bus bar number for the location, for the irradiance and in our location. So, for example, this may be like an extreme example, but if you have the main irradiance distribution at your location would be 500 watts per square meters, and it would be around 50%, then you obviously here maybe the 4 bus bars would be the main, the optimal amount of bus bars. But if the rest of the irradiance distribution would maybe have 30% of 1.7 suns, the 4 bus bars are not that optimal anymore, but maybe the 8 bus bar line would be the optimal amount for the cell. So that is like a calculation you need to do, which or which amount would make more sense to have the most efficiency. So for Brotas, we have here our irradiance distribution. You can see it on the secondary axis. And as in the slides before, you could see, we still have an irradiance of 30% that is higher, or still higher than 1,000 watts per square meters. And this line, or this data, is from the year 2019. So what we did basically now was to calculate the global efficiency, and we did that by multiplying the efficiency of every bus bar with the irradiance distribution and summed it up and got to this line. And that was where you need to remember my first slide from the results. We expected to have a much higher number of bus bars because of the amount of over-irradiance we have in Brazil. But in the end, we figured out it didn't really change that much, or it didn't have that much impact yet. It still has an optimal point at 5 bus bars, what was a little bit disappointing to find out. But yeah, we only changed the bus bar numbers yet. We didn't change the temperature of the cells. We didn't change the fingers of these cells. So these are all like data impacts that could, like, by further investigation, maybe change the result. So to have a final conclusion, here are the loss charts of the cell with 5 bus bars. One time at the standard test condition, and one time at the maximum irradiance level that we simulated at 1,800 watts per square meters. And because both of these loss diagrams are based on the 5 bus bars, we only focus on the resistance losses and not on the shadings losses. And you can see with the 5 bus bars that at standard test conditions the resistance losses are very, very low. I can tell you even the number of it. It has 0.58 milliwatts per square centimeter, and if you look at it at the maximum irradium we simulated, just be aware that the scale is different than here, so it's not quite that much of a difference, but it's still a huge difference. So that is because at this point, the cell is able to actually capture the whole irradiance energy that it gets from the irradiance, and here with the 1000, it's not able to capture everything anymore. And we end up with a resistance loss of 1.78 milliwatts per square meter. And yeah, so much higher than at the standard test conditions. And finally, we have I have a little summary of all of this. The results of this investigation will be published at the Brazilian Solar Energy Conference next May in Florianopolis, as a conference paper. Actually, the submission was today, but it got postponed to January 22nd. And it will contain that our optimal number of bus bars is 5 for the irradiance level in Brotas. And we were taking not only the standard test conditions in occurrence, we also took the over-irradiance occurrences into account for that. And what this investigation should lead to is that we need to figure out if a different if we can do different parameters, if we can vary different parameters, and if it would change the 5 bus bars to maybe even a higher number of the bus bars, and maybe to a different shape of the cells. Yes, so if you have any questions to me, you can ask them. Obrigada.